So this is the fourth and final podcast covering the energy, power and climate change in the IB Physics course. This podcast will focus on how the use of fossil fuels in particular has affected and continues to affect our climate through climate change and global warming. Our planet receives almost all of its energy and energy sources from the sun, and our planet is a nice livable place thanks to the energy of the sun. We can calculate the average power received by us from the sun, and essentially that is the brightness. If we think back to the astrophysics unit, in the astrophysics unit, brightness is the luminosity, which is the total power of the sun, divided by 4 pi r squared, where r is the distance, the average distance from the sun to the earth. Plug all those numbers in and we get this number, 1360 watts per meter squared. But this is of course above the atmosphere. This is when we can actually see the sun during daylight hours, and this is when the surface is perpendicular to the sun's rays, so the sun's rays are hitting it at 90-degree angle. Now if we average out that energy over the whole surface of the earth, considering the fact that not all of the earth is perpendicular to the sun's rays, of course, and also that 50% of the earth's surface doesn't receive any sunlight at any given time, by applying this ratio here, a better estimate is around 340 watts per meter squared on average over the whole surface of the earth. And of course some of this is going to be reflected and absorbed by the atmosphere. Now if we look at this map of North America, or United States of America, we can see that the color coding indicates how much energy actually gets through and reaches the ground. The red areas are the higher energy, and some places are getting up to 8 kilowatt hours per day, which equates to about 330 watts per meter squared. Whereas other places, cloudier areas, it gets much lower, with possibly as low as 80 watts per meter squared on average up in the higher latitudes. The concept of albedo deals with reflected energy. So not all of the radiation incident on a surface is absorbed and some is reflected. The amount reflected depends on this albedo, which is a reflection coefficient. It's defined as the reflected radiation divided by the incident radiation. So the ratio of reflected radiation to incident radiation. Average albedo for the Earth is about 0.3. But if we look at some specific examples, water we can see is very, very low, less than 0.1, which means that a very small amount is reflected compared to the incident radiation, which also tells us that water absorbs a lot of the incident radiation on it. Soil, forest, meadows, savanna, crops, all of these things have very low albedo. Snow, as we might guess, is a lot higher because it's quite reflective. Clouds are quite reflective as well. Ice, somewhere in between, and sand, etc. So keep in mind that high numbers indicate a high reflectivity, low numbers indicate a low reflection, so a high absorption. So the radiation that is not reflected is absorbed, and this absorption causes the Earth to heat up, and consequently the warming Earth will also re-radiate some of this energy. And this goes back to another aspect of astrophysics, black body theory, and you'll recognize these curves here as black body radiation curves. We've got a very peaky curve here, 6,000 Celsius. This one would be corresponding to the outer layers of the sun, but down here 30 degrees Celsius, something closer to the Earth's temperature, we can see that the peak is in the infrared, whereas for the sun the peak is in the visible spectrum. So most radiation which is emitted or re-emitted, re-radiated by the Earth, is in the infrared spectrum. So we're going back to the Stefan Boltzmann law, which is also there in astrophysics, where the power radiated by an object, such as the Earth or the Sun or anything which has a temperature, is given by the Stefan-Boltzmann constant multiplied by the surface area multiplied by the Kelvin temperature to the power of 4. So we could say that the power radiated per unit area divided through by area, and we have this simplified equation here. So that equation applies to perfect emitters or black bodies. Most objects, or all objects really, are not perfect emitters, but we can modify the equation by including a coefficient called the emissivity, which has a value between 0 and 1. 1 would be a perfect black body. So we end up with the equation power is equal to emissivity times the Stefan-Boltzmann constant multiplied by the area of the object multiplied by temperature to the power of 4. If it's power radiated per unit area, then we lose the area bit here. So the emissivity, this is the power radiated per meter squared of the surface at a given temperature divided by the power radiated by a black body at the same temperature. So it's the ratio of the power radiated divided by the power radiated by a black body. This also can be written as the power radiated by an object divided by the power absorbed by the object. So this table shows some emissivity values. We can see some things approaching 1. Black plastic, as you might imagine, is fairly close to a black body. Human skin, very high as well. Lower things, metals, shiny metals are even lower, very shiny metals. So the idea of albedo deals with reflected rays from the sun. Some is absorbed, and emissivity will allow us to calculate how much of that absorbed energy is re-radiated. And of this re-radiated energy, most of which is in the infrared spectrum, not all of it goes straight back out through the atmosphere. The Earth's atmosphere actually absorbs some of this infrared radiation. As a result of it, that absorption, the atmosphere will warm up, and again in turn it will re-radiate heat in random directions, some of which is back down towards the Earth, so the Earth will actually warm up as a result. So there's this back radiation from the atmosphere back to the Earth which warms it up. The atmosphere keeps our climate nice and warm for our needs to live. If we didn't have an atmosphere, it would be very, very cold during the night, very, very hot during the day, and it wouldn't be suitable for life. So the atmosphere keeps our climate livable. But enhanced greenhouse effect, when we add greenhouse gases to the atmosphere, is actually causing our climate to warm up too much. So the gases in our atmosphere that actually absorb some of this infrared radiation, which is passing out, or trying to pass out, water vapor has the greatest effect. Water vapor absorbs the infrared radiation. Cloud droplets, carbon dioxide, methane, and ozone. So we can see that the components of the greenhouse effect are natural. Water vapor is there naturally, and so is carbon dioxide, methane, and ozone. But we are adding to these parts here, carbon dioxide and methane. Our actions are increasing the percentages of these gases here. Linking back to the black body spectrum again, from Wien's law, we can see that taking the surface temperature, the average surface temperature of the Earth to be 294 Kelvin, we've got a maximum wavelength, a peak wavelength for the emitted radiation of around 10 to the negative 5 meters, so firmly placed in the infrared range. Now this graph here shows us black body emission spectra. We can see 320K, 300K, 280K here, and we can see the emission spectra for the Earth from above the atmosphere, and we can see that it's not appearing as a continuous black body, and there are clear dips in certain places. For example, this dip here is due to absorption of the infrared by carbon dioxide in the atmosphere. This dip here is due to water vapor. This dip here is due to ozone, O3. This dip here is due to methane, and this dip here is due to water. Here we can see that the emitted infrared radiation is as theory would predict. So this, we can call this an atmospheric window. Radiation of this wavelength here, which would be approximately 10 to 13 micrometers, passes straight through the atmosphere. It's a window, an atmospheric window. If we look at a broader picture, so this shows a much wider range from ultraviolet, visible, near infrared, thermal infrared, and this applies to incoming radiation, of course, as well as outgoing radiation. This wide hatched area here shows the range, which is also covered by the diagram on the previous page. This one here we can see from about 7 to 25 micrometers. About 7 to 25 micrometers. This other hatched area here corresponds to what I call the atmospheric window. This top graph here shows the total absorption and scattering. There's only a little bit of scattering, but mainly absorption of the different wavelengths. And this breaks it down. We can see water vapor, a lot of different wavelengths there. This is the main emission area for the Earth, the longer wavelength infrared. We can see that carbon dioxide plays an important part there. Oxygen and ozone smaller, methane smaller, nitrous oxide smaller. Rayleigh's scattering is the reason why the sky is blue, and we can see that scattering is only significant in the ultraviolet and just into the blue end of the visible spectrum here, which is why the sky is blue. This interesting map shows radiated power, September 2008. We can see that the equator is relatively low due to cloud cover. The tropics areas are higher because of less cloud, and we can see the polar regions have a very low outgoing heat level or radiated power. So eventually there must be a balance of incoming and outgoing radiation in a stable climate, and we can see this diagram here represents that. We've got the incoming solar radiation, 342 watts per meter squared, something similar to the average we calculated earlier on, and we can see some is reflected by clouds, some is absorbed by the atmosphere, this amount reaches the Earth, some is reflected by the Earth. Over on the right side here we can see the surface radiation, the long wavelength infrared, some of which passes through the atmospheric window, most of which is absorbed by the atmosphere, some of which is emitted by the atmosphere outwards, some of which is emitted by the atmosphere back down to the Earth's surface, and we can call that back radiation. We have small amounts of thermals and latent heat through evaporation and so on. And if you look at all these numbers, there's a balance there. We can see we've got 107 plus 235 is equal to 342. So the outgoing and the incoming balance. This balance can be achieved at different temperatures, and as we increase the greenhouse gases, this balance is being realized at higher climate temperatures. The surface temperature of the Earth is an important aspect in this, and it changes during day and night, of course. It's in constant flux, cloud, sun, day and night. We can use the concept of surface heat capacity, similar to specific heat capacity, to calculate the surface temperature required for this balance. So C suffix S is defined as the energy required to raise the temperature of a unit area by 1 Kelvin. So we have this equation. Surface heat capacity is equal to energy absorbed divided by the area and the change in temperature. If the outgoing radiation is less than the incoming radiation, then the planet will warm up. The difference between the incoming and the outgoing intensity multiplied by the time will give the net increase in energy per unit area. So rearranging this equation, we get this, which is in the data booklet. Change in temperature is equal to the incoming radiation minus the outgoing radiation, so that's the radiation absorbed, power absorbed, multiplied by the time to turn it into energy, Q, divided by the surface heat capacity. So the incoming, the incident radiation, multiplied by 1 minus the albedo, because we don't want to include the reflected portion. The outgoing radiation is the emissivity, multiplied by the Stefan-Boltzmann constant and T to the power 4, or alternatively the emissivity multiplied by the incident radiation. So we have ways to calculate these values. So let's look at a problem. So if the amount of radiation incident on the Earth's surface is 330 watts per meter squared, the average albedo is 0.33, and the emissivity is about 0.4, and a day lasts for 10 hours, and the surface heat capacity is this, calculate the rise in temperature of the Earth's surface in 1 day. Okay, so where do we start? We've got the albedo firstly, is reflected divided by the incident radiation. So we can rearrange this to find the reflected. Reflected is going to be the albedo multiplied by the incident radiation. So we have the albedo is 0.33 multiplied by the incident radiation, which is 330. So we have the which equals 109 watts per meter squared. So the absorbed radiation is going to be the incident radiation minus the reflected radiation, which equals 221 watts per meter squared. So continuing, so we can find out what the emitted radiation is. We've got emissivity is emitted radiation divided by the absorbed radiation. So we need to multiply the emissivity by the absorbed. So the emissivity is 0.4 multiplied by the absorbed, which is 221, which equals 88 watts per meter squared. So now we have the information we can plug straight into here to find the change in temperature. So we've got the incident radiation as 221 minus the outgoing radiation, which is 88. I'm going to multiply that by the time, which is 10 hours, multiplied by 60 minutes in an hour, and again by 60 seconds in a minute. And finally we're going to divide that by 2.08 times 10 to the 8 and see what we get. Equals 0.023 Kelvin. So not a great change there. But as the balance changes and the Earth absorbs more energy, then we do see this global trend, this global warming trend. This graph shows atmospheric composition of carbon dioxide, which has been recorded since 1950 something at Mauna Loa, which is on the island of Hawaii, in the Hawaiian Islands, and we can see that the amount of carbon dioxide in the atmosphere is going up rather rapidly. Looking at ice core samples back in history, back into the 1700s, we can see this trend has actually been continuing from back then, and since the mid-1800s, industrialization was initiated and lots more fossil fuels were burned, and this is increasing at an alarming rate. Essentially speaking, evidence shows that it is due to burning of fossil fuels, and it's a man-made thing. It's not due to solar flares or volcanoes, etc. It's enhanced global warming by human activity. So some examples of mechanisms that increase the rate of global warming. Melting ice caps. Ice has a relatively high albedo, water very low. So as we lose the ice caps, the average albedo of the Earth is going to get lower, which means more absorbed. Deforestation also is going to reduce the amount of carbon fixation in the foliage in the trees, which means more carbon dioxide in the atmosphere. As the climate changes and as ocean temperatures increase, unfortunately, the solubility of carbon dioxide in water also goes down. Water can take a lot of carbon dioxide in there, but as it warms up, it can take less. Also, rising sea levels are a concern on many levels, but increasing levels will increase the surface area of the oceans, and as the water has a low albedo, it means more energy will be absorbed. But why will sea levels rise? So we've got a couple of reasons. Melting land ice which is sitting on land masses like Greenland and Antarctica, as it's not floating, it's going to actually change the sea level. So here's a question: what increase in depth of the oceans will we expect if the land ice on Greenland and Antarctica were to melt? So we need to calculate the volume of ice on those two land masses, the average volume, estimate the volume, and just spread it out over the current ocean surface. So from Wikipedia, we've got the surface area of Antarctica and Greenland added together, average depth of ice, 3 kilometers. So the volume of ice, those two things multiplied together, gives you this large volume of ice. If we say that the average area of the oceans is about 70% of the planet, we can then use this equation. The ocean area times the change in depth is equal to the volume of ice. We can work out the change in sea level. So finish that calculation off. Done it? Good. Let's move on. So another reason that the sea levels can change is just simply by expansion. The oceans are going to warm up, and the coefficient of volume expansion is going to cause the volume to increase. Most things increase their volume as they warm up due to the spacing of the particles increasing. So the coefficient of volume expansion is the fractional change in volume of a substance per unit temperature change. So for water, this coefficient is 0.000214 per Kelvin. So what will be the change in sea level if the world's oceans were to warm by a fairly modest 2 degrees Celsius? Surface of the oceans, approximate volume of the oceans. So here we go. We've got this cube which represents the volume of the ocean, and we've got this rectangular area representing the surface, and we have this little chunk here representing the change in depth. So let's work it through. So the change in volume of the ocean is going to be given by the coefficient of volume expansion multiplied by the volume multiplied by the change in temperature. So we have the coefficient of volume expansion, which is 0.000214, multiplied by the volume, which is 1.3 times 10 to the 9, and multiplied by the temperature change, which is 2, which equals 556400 kilometers cubed. So the change in depth of the ocean is going to be given by the change in volume divided by the surface area. We're spreading it out over the surface area. So we've got the change in volume, which is 556400, divided by the surface area, 3.6 times 10 to the 8, which gives us 0.015 kilometers, which is equal to 15 meters, isn't it? 15 meters, so that's quite a lot. 2 degree temperature change. That's the whole of the ocean, of course, not just the surface layers, which is more likely to happen. But if the whole body of water were to change its temperature by 2 Celsius, we would get that temperature rise, that height rise rather. Now if we put those two steps together, we actually get change in depth is this divided by this. Because volume is surface area times depth, we actually end up with coefficient of volume expansion times depth times temperature change, which is independent of surface area. So it's actually the depth which is the important thing. If you do the same calculation for your bathtub, cooling by 20 Celsius, a far greater cooling, try it out. You're going to get a much smaller change in depth, very, very small, insignificant. You won't really notice it. But try the calculation out. Put in some suitable numbers. So this is a problem that needs to be solved. We can't keep on ignoring it. Possible ways which we can reduce this enhanced greenhouse effect: greater efficiency of power production. The maximum theoretical efficiency is governed by the Carnot cycle. If you look back to higher level thermodynamics, if you burn less fuel, you emit less carbon dioxide. Using more natural gas is going to help because natural gas emits less carbon dioxide. It burns more cleanly. Use of combined heating and power systems, or CHP, the heat that is dumped into the environment in thermal power stations could be channeled to heat homes, in which case you're not going to need to burn extra fuel to generate that heat. More renewable energy sources and nuclear power. Most of these don't emit carbon dioxide, so these are very good way to go. Capturing carbon dioxide, we can pump it underground. We pump the natural gas out, we could possibly pump the carbon dioxide underground, and this is being done on a small scale. Hybrid vehicles, we do burn a lot of oil in cars, and hybrid vehicles are way more efficient than regular vehicles. Finally, I'm going to set you some homework. You need to research some of the current ways that the global community are tackling the enhanced greenhouse effect climate change issues. The IB suggests that you look into the Intergovernmental Panel on Climate Change, the IPCC, the Kyoto Protocol, and the Asia-Pacific Partnership on Clean Development and Climate. So do some research, use the internet, find out what these organizations are doing. So that brings us to the end of energy, power, and climate change.